Hey, how are you doing, guys? I'm Lohan. Here's the sixth part one, which is about KeyPoints Regression and Hybridizing Models. So let's get started. Okay, so here's the outline. So first of all, we are going to discuss what exactly is KeyPoints Regression and how to implement it using fastai library. Then we are going to grab our dataset, clean it, and visualize it. And then we are going to build our data block and train our model. And in the last part of the lesson, we are going through hybridizing models. So let's get started with our lesson. Okay, so let's begin with key point regression task. So what is key point regression? Key point regression refers to the task of predicting the location of key points or landmarks on an image. These key points can be any identifiable feature on an image, such as facial landmarks like the corners of the eyes, nose and mouth, or the joints of a human body. So the goal of key point regression is to predict the x and y coordinates of these key points on an image, usually represented by a heat map or a set of vectors. This involves training a deep neural network to learn mapping between the input image and the corresponding set of key points. So the key point regression can be used for a variety of tasks, including facial recognition, pose estimation, and object tracking. And FastAI provides a range of tools and techniques for key point regression, including the ability to train models using convolutional neural networks and to visualize the predicted key points on an image. For this task, we are going to use the vision library from FastAI. And now let's take a look at the data that we are going to use. So we will use cat dataset on Kaggle. So the cat dataset includes over 9,000 cat images. For each image, there are annotations of the head of the cat with 9 points, 2 for eyes, 1 for mouth, and 6 for ears. So let's go back with our notebook. Okay, so here's the URL of the dataset. Then we use Google Down to download the dataset because it is stored in the Google Drive. And now let's unzip it using zip file. So here we import the zip file and then we extract our dataset. And now let's take a look at the folder. So we can see that we have the main cats folder and then we have cat underscore 5, 6, 2, 1, 3, 4, and 0. So we have some duplicate folders, so let's get rid of the cat underscore directory and just work out with the cats folder. So here we remove the duplicates from it. And now we are going to move all the files in each separate individual folder up one level. By this way, we don't have cat1, cat2. It's all just there because we don't care about classifying the cats. We just care about what key points on the cat are. So if we take a look at how they labeled, so let's go here. As you can see here, the annotation data are stored in a file with the name of the corresponding image plus .cat at the end. There is one annotation file for each cat image. So let's grab our images and the labels. So first we specify the path to the directory named cats where our data stored in. And to get our images, we are going to use get image files, pass it the path for the images that we defined in the above cell. And for our labels, we use get files that search for .cat extension. And here we want to make sure that we have a same number of labels and images. So now we are good to go. Now we should be okay. We have a label for each cat image. So let's make sure of that. So here we define image to key points function. So the function takes a file path f as an input and returns a string that represents the corresponding path to a file containing the key points for the input image file. Okay, so let's try this on an image. So we are going to use the first image as an example. So here we grab it and store it in a fName variable. Then we pass it to PIL image.create because we want to show it. And here's the image. And now let's grab some coordinates by using KeyPoints functions that we defined. So here we call image to KeyPoints function and pass it the first image that we grabbed. And to get the KeyPoints, we use NumPy to generate a NumPy array from a text file, and here is the returned array. So if we take a look at the returned array, it doesn't look like the KeyPoints because this could be an X and this could be an Y. But what does this line mean? So if we go back to Kaggle website, and under content is actually describes what's going on. So the order is, there is the number of points present, followed by left eye, right eye, mouth, left ear, and right ear. And now we need to separate our key points into pairs. So this is what separate points function is going to do. So it takes a bunch of coordinates and then go through and group them together into a tensor. And here we test it. And now let's put it all together through some sort of getY function for us to work with the tensor points. Now we made sure that all of our images have the associated key points with them. But what if the person that was building the dataset decided to label some images in invisible regions? That's exactly what happened to this dataset. So we need to figure out the way to go through and test all of the images and make sure that they open. And if they open, make sure that all of our points are within the visible range. And if any aren't, then go and set that away as a removal. So that's what this algorithm here does for us. It iterates through a list of image file names, and for each image file loaded into PIL image object using PIL image.create, retrieve the corresponding key points for the image using getY function, and then check each key point to see if its X and Y coordinates are within the bounds of the image. If the key points is outside the image bounds, add the image file name to a list of bad images. Let's take a look at how many bad images we had. So we have around 1400 images. And here we make sure that we don't have a repeat name by generating a set. So we have around 1000 more images. So in total we have around 1000 images whose points go out of the bounds. So there is a few different ways we can deal with this. First, we can remove the image or zero these points to -1 and -1 through a transform, or we can keep the points. So each of these has its benefit. So we will deal with the first one. So we are going to remove the image. So now we go ahead and clean our images by removing the bad images from our dataset. And here we grab our images by using getImageFiles as we did. And now let's go back to work with our tensor points. So we define this function that takes as input a PIL image object and an array of points. Then it goes ahead and creates a tensor point object from the input points and the size of the image. So here we have this 1 by 2 tensor that we expect. Then we pass the functions that we defined our first image and its key points and store the returns into TP variable here. And now let's try to visualize it. So as you can see, we need to pass in the access of our original image into TensorPoints.show function. And now we can see the key points of our cat image. And now let's go with the data block because the transforms get a bit tricky when it comes to deal with the tensor points. So the first thing that we are going to talk about is clamping, that clamps the points in a batch of tensor point data between a minimum and maximum value specified by the user. So let's consider this case. Random resize crop crops our image and makes the points goes off the screen. Do we keep the point and let the models guess, or adjust the point? Okay, so let's build a transform to adjust for this. So this is what clamp batch class is going to do. So if you need to read this code, so here it loops for every x in the patch, and then go through with every pair in this patch, clamp down with some minimum and maximum value. So here we set the minimum to -1 and maximum to 1. And any of our values above 1 or below -1, then default it to -1 and -1. Let's go ahead and run clamp batch. So here we define our item transforms and batch transforms. And as you can see, item transforms contains a single transformation resize that squashes the input image to a size of 448 while preserving its aspect ratio. And for batch transform contains a several transformations. As you see, it includes flip, rotate, zoom, and wrap. So here's a nice list of all of the key point arguments that are available. Then we define our data block. So image block and point block specifies that the input data consists of images and their corresponding point labels. And for get items, here we specify that the input data will be loaded from image files. And we are going to use random splitter that splits our data into training and validation randomly. And then we define our get y and the transformations that we saw above. And here we define our batch size to be equal to 24. Okay, so before we even do a show batch, we need to call the summary method to make sure that we're getting some y's first, and this y's looks accurate, and then the show batch will be the final step. So here we call .summary and pass it the folder, so it was in the paste directory in Colab, so this is why we passed this single code here. And here's the results. So as you can see, we don't have any issue. Then we build our data loader. And here we show a batch, and as you can see that all of our key points relatively match up. So if they don't, that's because of human error. And here we give it .c attribute so we can create our model's output easier. And as you can see, we have 18 classes. Then let's go through and generate a custom model and head for regression. So now we know our outputs and inputs, so we can make use of two functions, create body and create head, that we covered in details in the previous video. As you can see here, we use a body of ResNet 18. And if we looked at the very last block of the body, we will see that the output is 512. And now let's make our head. So every time we generate a head in fastai, we have two pooling layers, adaptive average pooling and adaptive max pooling. It doesn't mean that our output goes to adaptive average pooling and then adaptive max pooling. Instead, our output go to both of them at once. So that's why our input was 512 and here we're expecting 1024. And then we declare our output to be 18 total targets. Then we wrap our body and head in a NN.sequential object. And now we can split it. So this function takes a ResNet model M as an input and splits its layers into 3 groups for using transfer learning. The first group here includes the first 6 layers for ResNet model, which are responsible for extracting low-level features such as edges and corners. The second group includes the remaining layers for ResNet model, which are responsible for extracting high-level features and learning to classify these features. And the third group includes the fully connected layers added to the ResNet model for classification. So if you look at archive 1, it's just the head of our model. And finally, we initialize our model by using Kalman normal distribution. And now we are done. So we can make our learner pass it our data loaders, the architecture, and the loss function. So here we use the mean squared error. And then we pass it our splitter, and we are going to use ranger as our optimizer. Then we can freeze like CNN learner does. And we are going to use a learning rate with 10 to the power negative 2. And train for 5 epochs by using fit-flat cosine function. And here's our results. So as you can see, it's not that bad after just 5 epochs. And then we can unfreeze and find another learning rate. Then we train with 5 epochs. And as you can see here, the result gets better. And now let's go with the second notebook, which is about hybridizing models. In this notebook, I will show you how you can modify any architecture to fit any problem. So in our example, we will utilize a unit architecture to do keypoint regression, multi-label classification, and regular classification. And here we just prepare our data exactly how we did before. So fastai unit generates from this unit learner function, and we are going through and try to understand where we need to adjust our model to give it this sort of custom head that we need to strap on for almost any task. So how we are reading this, as you can see here we have arch, and at some point it calls create body. So if we track where create body lands to, as you can see we get models.unit.dynamic unit. So this is generating the head of the model and the rest of the unit. So we are going to try and adjust that to make it more custom unit. So the line that we are going to change is this line. So instead of dynamic unit, we will call a custom unit. And this goes ahead and grabs the helper functions that unit learner will need. So this is the custom unit. And the main bits that we are going to look at here is we don't want to touch anything else except the last layer that before the output layer. So the specific layer that we want to get rid of is the last conv layer here because this calls the number of classes. So let's go through and try to generalize generating this output. Now create head needs the output size of the last layer. So we can grab the number of feature model and pass it one particular layer. and it will get the output size of this layer. So here we call the last layer, and we want two of them because remember that we have two pooling layers. Then we can create a head. This is the number of filters and the number of classes, and we got to go. So now instead of using unit for segmentation, we can use it for key points regression. Now we are going to make our custom unit function that calls our custom unit model. Otherwise, everything else is going to be pretty much the same. So here we call our custom unit, pass it our data loaders, our ResNet34 architecture, and our loss function. And another way to make sure that we haven't broken anything before we started training is to call learn.summary. And as you can see here, we don't have any error. And now we can find our learning rate. And we are going to fit with 3 epochs. And as you can see here, our results are so good. So this is just a creative example to show you guys don't be afraid to think out of the box. And here's another examples of applying our custom unit to classification and multi-label, so you can play with them. And that's it for today's video. Hope you enjoyed.